Thank you, Mikko. So yeah, to the millimeter waves then. In the automotive industry, millimeter wave radar is used for accurate sensing of location, velocity, and angle. It's a primary part of advanced driver assistance system and autonomous vehicle, along with the ultra-wideband radars, like Mikko explained before. Millimeter wave radars are used in live detection and parking assistance, and in a lot more of other applications. So on the next slide, we can see that on the such high frequencies, simulation with the environments become really tricky. But also you cannot just neglect environment. On these frequencies, you really want to take into account environments. And a full car model can be around 1000 wavelength at 77 gigahertz, which makes, as you can imagine, mesh will be very, very dense. Luckily, for example, for as shown here, front bumper radar, you don't usually need the whole car. You just need some front part of the car, but it's still very huge structure compared to size of the antenna on this frequency. The metal environment adds a lot of complexity, and because as you can imagine, the car is not just metal box; it has a lot of different surfaces. So if you want to go with the one solver, that will result in very, very, very dense meshing. And on the next slide, we can see that on millimeter wave, we have one more thing that we need to consider, the radon. So the radon effects is one more new thing that affects antenna a lot on that frequencies. So in the beginning with the shark fin antenna, we also had radon, but on the 900 megahertz frequency, you just need to simulate. You just need to know the dielectric, qualities of the material and then the size, and that's all. You don't need to worry so much about that. But on millimeter waves, it affects antenna a lot. And using assembly and hybrid solver method, it can be possible to split the full simulation model into 3 subdomains. So we will have antenna in open space, we will have radom, and we will have a car, or just the front part of the car, for example, bumper, or so. And with this approach, we can save time on resimulating antenna all the time. And you can think about a lot of applications when you can benefit from that. For example, when you want to take into account thickness of radom. So you already have your millimeter wave antenna simulated, and then you just change the, for example, you have parameter sweep on the thickness of dielectric of your radom or epsilon, and you don't need to resimulate antenna already, because it has already fields from previous simulation that you've done with the hybrid solver. So you only simulate very limited part where antenna actually touch, with the fields actually touch the radom. And that saves a lot of time. And then when you find this optimal size or thickness of the radom, you can now start to play with the placement of the antenna. And now you already have your antenna radom simulated one time, and you place it with the hybrid solver using anchors. You place it to the car, and then you can sweep the position as well, and see how the position affects antenna. antenna efficiency or performance. And that's also very useful when performing tolerance analysis, because on these frequencies, as you can think, tolerances affect a lot. Thickness of dielectric for printed antennas. Again, tolerances in your radome. That all will affect a lot on the final results. What you actually get in real life can not match your simulation, because if you just simulated some perfect case scenario without taking into account any tolerances, then probably it won't be the same. And yeah, lastly, let's talk a bit about encryption. So this is a bit different topic, but it's also very much connected to, of course, automotive and hybrid solver. So it's not unusual for automotive companies to use encrypted models, especially when working with the third-party subcontractors. You can think that, of course, companies like automotive companies, they don't want to just share on left and right their new developing models of the cars. They want to keep this it's secret before the release. And that's where we can actually have encryption. So if you now can see that this is our car, that's I showed before. We used it with the Mikko in all simulation, and this is the fully encrypted version. How it's a bit funny looking, boxy, but inside this. So if I get this model as antenna engineer, I cannot with any means, I cannot see what's behind these boxes. But the software knows what behind these boxes, and it knows the material, it knows sizes and so on. So I can work with that. But probably for unprepared engineer, it's a bit tricky. So that's why, if we can see on the next slide, we can actually have partly encrypted model. So in this case, if we want to simulate, for example, this shark fin antenna that I explained in the beginning, if we want to get the encrypted model, and for example, we want to simulate the best antenna placement, and we have, for example, a roof open. So this is and we can play with that, but we cannot see other parts. And of course, that can be applied for every model, every part of the car that you can see. It can be less encrypted, it can be more encrypted. And yeah, so as I said, for this approach, hybrid solver works exactly the same. So you can do with this model the same as we with Mikko showed you before. You can use it as a block, as a domain with the hybrid solver. You can place anchors on the roof, for example, with this case. If we now go again to that case in the beginning that I said about shark fin antennas. So we have some anchors on the roof. We have a separate domain for shark fin antenna, and we apply hybrid solver, some time domain or frequency domain for shark fin antenna, and for example, asymptotic solver for whole model. And we can sweep position of antenna on the roof that we can see here. And it works perfectly fine. And both parties, automotive company who wants to keep secret and encrypted their model, and antenna engineer that wants to have good and reliable simulation, both parties happy. And that's why we can confidently use this approach as well. That's all that I have for encryption. Thank you very much.